All right. Good afternoon, everyone. Thank you all for being here today. And in case you don't know me, I'm Hanzhi. I'm one of the co-founders of Nubit. And I'm also a PhD student at UCSB, where I do research in blockchain security and ZK technology. So today, I'm going to introduce our recent work on push-button verification for BitVM implications. So let's get started. First of all, everybody is celebrating the bull market where Bitcoin is hitting all-time highs again. And however, despite introduced in the same paper by Satoshi, Bitcoin as the currency and the Bitcoin network are like two opposite extremes. So on one side, Bitcoin dominates over 60% of the market share and with over 20 billion daily volume. And on the other hand, Bitcoin as the network can only handle 4 transactions per second. And how many can Visa handle? It's 24,000 per second. So that's a huge gap. And given the previous numbers, it's not very hard to understand whilst there are like hundreds of Bitcoin ecosystem projects early last year, such as Layer 2, Oracles, DeFi's, and none of them went very far due to this brutal limit of Bitcoin. And with, let's say, ordinals and inscriptions, we immediately see the consequence of the limitation via network congestions and rising fees. So there are also many Bitcoin native projects, including a bunch of Layer 2s, DeFi's. They claim to solve this problem. And however, if you analyze their data flow, none of them goes far beyond their own centralized servers. It's because getting their transactions settled on the Bitcoin network is not only expensive, but technically highly non-trivial. So what can we do? Luckily, we got BitVM, originally proposed by Robin Linus 2 years ago. It was born to address this limitation. So the high-level idea of BitVM is very easy to understand. So since the computation power of Bitcoin is both expensive and limited, so let's move the heavy lifting computations off-chain and only defer the on-chain validation process with an on-chain verifier deployed on Bitcoin. So you only need to trust science and like Bitcoin network instead of any third parties or centralized providers. It's much like an optimist way to verify computations on Bitcoin. And with BitVM, the future looks awesome, right? But why we haven't seen anything yet? Well, because making BitVM from a prototype in the paper to a product is highly non-trivial. It's extremely challenging. So why? It's because Bitcoin script is not Turing complete. Just like any programs, you first have to implement BitVM. Let's say we pick a Glock 16 verifier for ZK snark in some high-level program languages, such as Rust. It is pretty simple. It's easy, as you can only need to write a few hundred lines of code due to there are already very sophisticated libraries, such as Arcwork. And since this program needs to be processed by a compiler to an IR, and all the way down to its low-level Bitcoin script. And now I hope you can understand, notice the issue. So why? We all know that Bitcoin script is Turing incomplete. And you may ask, what do you mean exactly? So, well, if you think of the expressiveness of EVM bytecode as A dots, who can express her rich emotions, such as happy, sad, angry, the expressiveness of Bitcoin script is like a 1-year-old baby who can only has 2 states, cry and not cry. So that means translate such a small program, ZK verifier into Bitcoin could be extremely large. For Glock 16 verifier, it will take 1 gigabyte of data. And manually construct such a complex and large program may highly possibly introduce security vulnerabilities. So what we can do? So to solve this problem, to ensure the correctness of such program, we need a proper formal verification tool for Bitcoin script. So our key idea is simple. So we want to automatically verify Bitcoin script, BitVM implementations, So it's very low level, that relies on some complex stack operations. So instead of manually checking this code, our approach translates this low-level Bitcoin script into a higher-level, clear representation. And then, like you can think of it as like converting this dense technical instruction manual into some plain language instructions that are much easier to understand and verify for computer. So the first stage of the whole process is to convert Bitcoin script into what we call a domain-specific language, or DSL. So this DSL abstracts away the messy details of stack operations by replacing them with register-like operations. So imagine you have like a complicated card trick that involves reordering cards in a very precise way. So our conversion process takes that complex procedure and rewrites it as simple steps like add, copy, move, much like clear instructions. So this results in a cleaner, a simplified version of the original Bitcoin script that we can analyze much more easily. And after we have this high-level DSL, the next phase is to automatically verify this code. So this is where we check that the converted code meets its intended behavior. So we use techniques such as loop invariant and symbolic execution. So the core contribution here is the loop invariant. So the loop invariants are conditions that must hold true before and after each iteration of a loop. So by summarizing the effect of repeated operations with a loop invariant, we capture the essential behavior of the code without having to like inspect every single step. So this can make the whole process more scalable. And imagine you put a giant Bitcoin script with millions lines of code, since there's no control flow, and you need to unroll all the loops. And this would be a disaster for the symbolic execution. So with loop invariant, to summarize the behavior, the solving time can be much less than the vanilla way. So together with these methods, loop invariant, symbolic execution, and the high-level DSL, we simplify the verification conditions significantly, allow our tool to automatically confirm that the specific Bitcoin script is correct. So essentially, we are taking a very complex set of instructions and reduce it to a clear logical statements that is much easier for the solvers to verify. And now let's look at some concrete examples. The first example is the big int multiplication. So big int multiplication is a crypto operation that's used in many blockchain protocols. It is used to handle very large numbers. Numbers are so big that they can be processed with standard types. So it is used in BitVM, in CK proof, in ETHDenver. Basically, every single crypto protocol needs this operation. And in the original Bitcoin script, to implement this big int multiplication is extremely hard. As seen on the left-hand side, the script must manually handle each limb of the large numbers. Essentially, it's the trunks of the large big integer, and it uses a series of stack manipulations like duplication, rotation, shifts, and it also needs to track all these operations by hand, which makes it super hard to verify. And using our tool, we first convert this low-level script into our high-level DSL. So in this representation, the sequence of stack operations is abstracted into clear, higher-level instructions on the right-hand side. So for example, instead of repeatedly moving pieces around, our DSL expresses the entire multiplication using a loop that updates two key variables. So one represents the current result, and the other represents the multiplicand, and which doubled at each step. And a loop invariant is then established to capture the relationship between these variables after each iteration. So this invariant states in simple term, the result so far equals to the original multiplicand multiplied by the process bits of the multiplier. So with this concise summary, so our verification tool can quickly check that the entire multiplication is performed correctly without getting lost in the low-level Bitcoin script details. And our tool is blazing fast. So we can talk about our experimental results. So we evaluate our verification tool on 78 different benchmarks from BitVM, and the results is kind of promising. So our tool successfully verified 83% of all the cases, and the average verification time per benchmark was just 12 seconds. And this tool, we compare this tool with the vanilla solutions, which simply convert the Bitcoin script into verification conditions without any looping invariants and inference. It shows faster verification time and can solve much better benchmarks. And importantly, our tool also identified a previously unknown vulnerability. So for example, here on the left-hand side, there is a buggy implementation of is positive, which will count 0 as a positive number, which is wrong. So and on the right-hand side, it is the fixed version. And this bug is discovered using our tool. To summarize, our work push-button verification for Bitcoin script basically simplifies and automates the verification of Bitcoin scripts, and which shows practical impact on improving the security of real-world applications such as BitVM. So if you are interested in our work, feel free to scan the QR code above, and have a nice day. Thanks for listening.